All right, Calc 3, welcome. It's Thursday, September 9th, and it's our first day of week 4 and our last day of week 4, right? Hope you enjoyed your Labor Day break, enjoying not having a video or a class on Tuesday. But we're back, and sadly, we're back for long term now, right? Because our next day off, unfortunately, isn't until Thanksgiving, which is literally in November, right? Of course. Anyway, let's not talk much about that. All right. So let's get moving on. We were finished, I think, with 11.5. And so if you have any homework questions, let me know in an email. And I'd like to be able to do some homework problems on next week's video if we have any questions on 11.5, because there's some homework problems that might be quite tricky in 11.5. So I'd like you to be able to look at that and then make sure that you are okay with that. And let me know if you have any questions with homework problems or you would like to see one on the video, yeah? Meanwhile, we're going to move on to 11.6, the next one, and talking about surfaces in 3D space. So I'm talking about surfaces. 11.6, surfaces in 3D space. Okay, so we definitely have a couple of surfaces that we have talked about in 3 dimensions, right? We've talked about planes, right? And we even have an equation of a plane, right? We know that the form of a plane looks like some number ax plus some number b times y plus some number c times z plus some number d equals 0. Right, that's the one of the forms of the standard equation of a plane, right? We also have dealt with other surfaces. We've dealt with spheres, right? So spheres are surfaces in 3D, and we even have an equation for those, right? X minus x naught squared plus y minus y naught squared plus z minus z naught squared equals r squared. So we have a couple examples of surfaces. I'd like to talk today about a third type of surface, and they're called cylindrical surfaces, or sometimes just known as a cylinder. So these are going to be familiar but new in a way as well. A cylindrical surface, or just simply a cylinder. Right? Now, when I say cylinder, I'm sure the classic cylinder, this, pops into your mind, right? You think of a tin can, right? Like that, yeah? And oddly enough, a mathematician just says this is one type of cylinder. There are many, many other types of cylinders out there. And so what makes this a cylinder? Why do we call it a cylinder? Yeah? Because really, what this full name of this is it's a right circular cylinder. Right? And I mean, of course, when you just say cylinder, you probably think just this. But cylinder is actually a more generic, more general term. The right word comes from that it makes a 90-degree angle with the base. Right? Then it makes a 90-degree angle, so it's standing like perpendicular, orthogonal to the base. Right? It's not tilted like this. If it was, it would be an oblique versus a right. Circular is referring to the shape that is used to generate the cylinder. So the base is circular, and so we say that that is a right circular. And then it comes down to cylinder. What is the action that one performs to generate or create a cylinder? And I imagine that maybe not many of you have thought about this, right? So what makes a cylinder by definition is taking a curve of some sort. Often we take a circle. You make a circle, and then you take a line that is maybe, that you move orthogonally to that. And so you make stack upon stack upon stack of circles. And what that does is generate what we call a cylinder. But there's no requirement for a cylinder in general to be drawn with circles. I could draw it with rectangles and have a right rectangular cylinder. right? I could have any shape. I could have that as a curve and draw it out as a cylinder. So let me go ahead and write down a definition, right? And then I'm going to show you what we can say is our cylinders, and so sort of expand and generalize what we mean by that word. So the definition of a cylinder is the following. Let C be a curve in a plane. Okay, so that curve could be circular, could be rectangular, could be this sort of sine wave thing that I got going on, right? And let L, capital L, be a line not in a parallel plane. Okay? So maybe L is this straight up and down line coming out of the piece of paper, right, like that. Or maybe it goes off at an angle like that, right? The only requirement is that L can't be parallel to the plane that the curve is in. Okay? Now, given those two things, a C, a curve, and some line not in a parallel plane, we can now say the set, collect all the points, set of all lines parallel to L and intersecting C is a cylinder. Okay, take a moment to read that again. The set of all lines parallel to line L and intersecting the curve C is a cylinder. So remember my example here. Suppose I have a circle. Right? That circle lives in a plane like that. And my line is the line that points straight up. Right? The line that points straight up here. Now draw every parallel line that goes through that circle. See that? And you would generate the very familiar cylindrical shape that you're used to, right? So in other words, think about, here's L, this is the line, this is the circle, and so you're getting lines like this. And you basically generate all lines parallel to that, and it draws the shape that you get. That's why this is a cylinder, right? It's not the circle that makes it a cylinder. It's the idea of these lines, right, going through that curve, generating like a circle upon circle upon circle, a stack of circles, if you will, creating a surface in 3D. Yeah. And so here, I could do this, right? I could have a rectangular cylinder. I know that sounds really strange, but isn't that the same idea? Take a line that goes like straight up here and take all of those copies, right? And you would get walls, right? You would get walls like that. Now, they might they might not like this specifically because of the corners, right? So their definition of curve might require the corners to be sort of rounded. So maybe to back off a little bit of that, maybe we could say we have a rounded rectangle, something like that. That would generate a cylinder, right? But this would also generate a cylinder. This is a shape, this is a curve, right? And we could take straight lines, and now I have like this sine wave wall, like a wall of sine wave, right? Like that. That would end up being a cylindrical surface, all right? So let me show you. I think I did something in GeoGebra here. Yes, I did. Yeah, so in GeoGebra here, what I can do is, suppose I draw a curve. Oh, that doesn't show up very nicely. Let's see if I can do better. Yeah, there we go. So let's say I generate this curve right here. See that? And so this is a curve in 3D, right? And it lives in the plane. It lives in the XZ plane, right? It lives on that left wall, if you will, right? It lives there. Now imagine, if you will, drawing this curve along a certain line. Maybe I want to draw them like horizontally this way. And so I've made it do that like this by just thinking of it like that. See this? And now think about making copies of this curve right? Making copies of this curve, creating a surface as you go. So I can emulate that in GeoGebra by just turning on the trace, right? So you can say trace here, boom, and now I can move this, and it'll remember where it's been. See that? And it draws this cylindrical shape, right? It's like a sinusoidal cylinder, yeah? And so if I move it here, see that? It's like a surface now that you can work with, right? And in fact, let's do this all together. I'm going to reset the view here. Okay, bring it back over here. Turn off the trace because it looks a little ugly when I do that. Okay, and then I kind of know ahead of time what this equation is. And so this is what I generate. See that? That surface right there. Okay? And so that is an idea, that is an example of a cylinder. Awesome. So we will often work with cylinders and their equations, right? So now the question is, what are the equations? What do cylinders look like on paper, right, for formulas? How, in other words, can I look at an equation, right, that's a three-dimensional equation there, and say, hey, that's a cylinder? Is there a way to be able to do that, right? So let's talk a little bit about how that would work. And since you have to be parallel to a line, right, there's a nice way to think about this. Let's go to the textbook here. And they say it really straightforwardly here. The equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the two other axes. Okay? Now what that means basically is if you are missing a variable, suppose you have x, y, and z, but z is missing. Now you have just x and y, that's going to generate a cylinder, right? If you have x, y, z, but you're missing a y, then that's going to generate a cylinder. So basically, if you're missing a variable out of x, y, and z, what that means is that variable can be any number it wants to be, and it's going to generate that same curve no matter what value that missing variable is, right? So at 0, it draws the curve. At 1 unit later, it draws the same curve. At 2, at 3, at 4, it draws the same curve. And so when a variable is missing, you're going to think of it drawing that curve, but at every one of the values of the missing variable, right? So to put this on paper, let's see what we can say. Let's look at the first thing we can sketch here. And I'm going to actually try to sketch this by hand slightly, just to get a feel for this first one. Of course, we'll get this into GeoGebra pretty soon, yeah? But yeah, let's take a look here. Let's sketch the cylinder. Z equals y squared. Okay. So z equals y squared in a three-dimensional context is missing an x. You see that? So I'm going to say, note, x is missing. Right? There's no x value here. So I'm going to get this curve when x is 0, when x is 0.5, when x is 1, when x is 2, when x is 3. So no matter what x value I'm at, I'm going to get what this curve is. Okay? So to get an example on paper, how can I draw that? Well, let's go ahead and draw our 3D coordinate system, our x-axis, our y-axis, our z-axis. And let's think of x being 0 for the moment, right? If x is 0, that means I'm living in the yz plane, right? And so in the yz plane, z equals y squared looks like a parabola, right? Because, if z is 0, for instance, y has to be 0, right? If y is 1, so if I'm 1 unit over, here, z has to be 1 squared, right? So that's going to be 1 as well. So that's going to be at 1, 1, something like that, right? And then if y is 2, right, then z is 4, 2 squared. Yeah? So 2, 3, 4. Right? And you get that very common parabolic shape, right? And in fact, I'm going to get it over here as well on the left side, right? Like that. Okay? Like that. So when x is 0, I get this parabola. But when x is 1, I also get the parabola. So guess what? I get a copy at x equals 1. So it's like this parabola again. Right? Yeah. And at x equals 2, and at x equals 3, and at x equals 4, and at x equals 5, and all of these x values along the way, I get this parabola, and I'm just going to get like all the way down drawing a surface. So at the end, I get something that looks like this, like that, and that's going to end up being something like that. So I get like this parabolic trough, if you will, right? Can't draw that well, but hopefully you see that, right? That's the idea there. So now let's go to GeoGebra and see how we can work with that, yeah? So going to GeoGebra here, let's get rid of this and this and this and that. Okay. And standard view, there we go. Okay. Now, I'm just going to type in the 3D sense. I'm going to click on the 3D graphics here and type in z equals y squared. Now, GeoGebra takes that to mean, oh, you tried to graph that in a three-dimensional sense, and so I recognize that x is missing, and it goes ahead and draws that cylinder. Do you see that? And so, yep, that makes sense, I hope. Any questions with how I did that? Right? So a way to draw a cylinder is to draw it in a single plane. Think of it as the two-dimensional plane and draw it there. And then you just draw copies of it up and down, or left and right, or up and down, depending on whatever variable you're missing. Right? So, for example, what about this cylinder? Right, if I said x squared plus y squared equals 4. Okay. Now you might look at that and say, wait a minute, that's a circle. Ah, under what context? Right? If I know my context is two-dimensional, then you're right. This is a circle centered at the origin with radius 2. However, if we're in the context of three-dimensional space, this is a cylinder because the z is missing. See that? And so since z is missing, I'm going to get a copy of this at every z value. So when z is 0, when I'm in the xy plane, I'm going to get a circle. When z is 1, I'm going to get a circle. When z is 2, when z is 3, when z is 4, I'm going to get circles. This is our standard right circular cylinder, isn't it? And in fact, the radius is 2, and the height is infinite, right? Because z is not restricted here, right? So to draw something like this, I might take something like this, draw my axes like this, right? And let's see, let's go ahead and put both sides there. And so I do 1, 2, 1, 2, 1, 2, and then 1, 2, right? And I go ahead and do a rough sketch of a circle, but in perspective, right? Something like that, something like this, and then something like that, right? And now I know that I'm going to get copies of this circle all the way up. So there's going to be even a copy up here. So I just sort of make a copy of that there, copy of that there. And I know that I'm just going to get stack upon stack upon stack of circles of radius 2, forming a cylinder. See that? Okay. How are we doing with that? Any questions with that? Awesome. What do you make of this? Z equals sine of x. Well, again, in a 3D context, y is missing. Y is missing. So one way to approach this is to think of this in the xz plane, what it would look like in the xz plane, and then just make copies of that, right? And so if I was to do a hand sketch, I would have to do something like x, y, z, right? So I'm in the xz plane, and I know sine would be this, like that, and I know it would go up like this, and then go down like that, go up like this, go down like that, something like that, right? And I would have copies of this all the way down the y-axis, like this, right? So the bottom here, the bottom there, and now my art skills are really hurting. So copy this like that, maybe. Oh boy. Right? I'm glad I have GeoGebra. Yeah? But anyway, that generates the cylinder. And that is the picture I was showing you earlier. Right? So we could say z equals sine of x is this right here. And there you have it, right? So you're going to take that sine wave and make copies all the way down. That's how we handle cylinders. Okay? And so sometimes we can graph certain cylinders by hand, get at least a rough idea of what that should look like. Yeah? Awesome. Now, the next type of surface, next family of surfaces, is the three-dimensional analog of conic sections. Yeah? Conic sections, the sections of a cone, right? And so these are called quadric surfaces. Ooh, let's get this down here. So we have quadric surfaces. And they're basically the 3D analog to conic sections. Right, and maybe you remember your conic sections, at least maybe hopefully the form or the equations of your conic sections, yeah? So for instance, right, so review real quick, conic sections. At least just recognizing the form of them, right? So if I had something like x squared over a squared plus y squared over b squared, and that equals 1, I hope that you recognize that that equation produces an ellipse, right? If a and b are the same value, you can then multiply it by that same value and you get a circle, right? You'd get x squared plus y squared equals whatever that value squared downstairs is, yeah? But this in general tells me that we have an ellipse in two-dimensional space, right? You could have hyperbolas. Hyperbolas generally have this form, right? This is a hyperbola, right? And then we have parabolas. Parabolas generally have this form, either y equals something x squared or x equals something y squared, something like that, right? These are sort of imbalanced. There's a power of 1 and a power of 2, or vice versa. These form parabolas. Okay. So if you recognize those, quadric surfaces are not going to be terrible. Now, what's hilarious, though, is look at the definition of a quadric surface. So let's take a look here. This always freaks students out. Look at this. Look at this definition. Okay. So it says, the equation of a quadric surface in space is a... Oh, it doesn't even fit on the screen. Hold on. The equation of a quadric surface in space is a second-degree equation. Okay, so that means that the highest power on anything is going to be 2, and that the sum of powers can't be more than 2. Yeah? In 3 variables, the general form of the equation is this: ax squared plus by squared plus cz squared plus dxy plus exz plus fyz plus gx plus hy plus iz plus j equals 0. All right? And so all this is saying is that any combination of these things, if you have like x squared terms, y squared terms, z squared terms, or you're allowed to have one of the variables and another one of the variables. So this is all combinations. You can have xy, xz, or yz, right? Because remember, powers can only be at most 2. And so here's power of 1, so that's your maximum power. Or you can have powers of 1, which is just would give me an x term or a y term or a z term. Or you could have powers of 0, which would just be a constant. And so if you allow for all of these, then you have what we have called a quadric surface, right? So, yeah. What we have here, and there's basically 6 types of quadric surfaces, and they all have their names. You're not going to ever be tested on what are the names of these, but we are going to work with a little bit how to work with them, right? So it won't be necessary for you to know ellipsoid, hyperboloid of one sheet by name, hyperboloid of 2 sheets, elliptic cones, elliptic paraboloids, and hyperbolic paraboloids. You will see that the names actually do sort of make sense, but it's not like a quiz where you're going to be like, name this thing, name that thing. I'd rather you be able to work with the formulas and recognize that it's a quadric surface, or recognize that, yep, we worked with those sorts of things. So that's more important than just memorizing the labels associated with that, right? So to visualize quadric surfaces, what we end up doing is utilizing what we call the traces of the surface. Now, traces are making one of the 3 variables a constant temporarily. And usually that constant is 0, right? So for example, here is an example of a quadric surface. X squared over a squared plus y squared over b squared plus z squared over c squared equals 1. That is an example of a quadric surface, right? There's a constant out in front times x to the second power, that's legit, plus a number times y squared plus a number times z squared equals a constant. So that fits the form of a quadric surface, right? Now, if I wanted to visualize what this was without GeoGebra, right, without an assistance here, we can utilize what we call the traces and see what sort of shape we get. Okay, so suppose for a second here that z equals 0. Okay, if z equals 0, what plane am I in? Well, if z is 0, I am in the xy plane, right? Now think about what this boils down to when z is 0. When z is 0, look what sort of shape I get. I get x squared over a squared plus y squared over b squared, z squared, so z is 0, that's gone, and that equals 1. Do you recognize that the trace of this shape, whatever it looks like, when I cut it with the xy plane, intersect it with the xy plane, its trace, its intersect, is an ellipse. All right? So that means in some sense, right, that it has an elliptical waist, if you will, like a middle part, right? The xy, when I cut this with the xy plane, it looks elliptical. Okay? Now let's do the other traces. What if y is 0? If y is 0, I'm looking in the xz plane. So the xz plane is the one on the left. Yeah. Then, with that said, y is 0. Notice what happens when that term is gone. I get an ellipse. X squared over a squared plus z squared over c squared equals 1. This is an ellipse. That means when I chop it with this plane, the xz plane, this surface, I also get an ellipse. So it's an ellipse this way, and now it's an ellipse this way. Right? Let's do the final trace. X equals 0. If x is 0, look at this. I end up getting an ellipse. So no matter how I slice it, I literally get an ellipse in all of the coordinate axes traces, right? And so this helps me visualize what this is going to look like. It's going to look elliptical this way, right? And elliptical this way, right? So this way, and this way. Ellipses all the way around, right? And so we call this an ellipsoid. That's the name for this for probably obvious reasons, right? Because every cross-section is elliptical. Right? Now, to show us in the textbook, their lovely picture of this, we get that idea. See that? Right? So when I just sort of think about the traces, this is like making like a wire diagram, right? Like just constructing a wire frame. So you can sort of get a sense of what this should look like, right? Now, how wide these ellipses are depends on the A, the B, and the C, right? You might remember from your conic sections that if A is like 2 or something, right, that means that X is going to be stuck, right, between that, because, check this out, right? Remember, this is a positive term, plus a positive term, plus a positive term, and they have to add up to 1, right? So think about it this way. If A is 2 and X is 2, do you see how that's already 1? And that forces these to be 0. You see that? So what that tells me is that the maximum furthest distance out that I can go x-wise, if A is 2, is 2. So that means that my x values go between -2 and 2. Right? And so the A, B, and C play the role of determining how large, how far out these ellipses go. Right? That's their role in this formula. See that? Now, do you see the general way that we can work with this? It's more important than just knowing the name, right? But if I see this, I can get a lot of information just by looking at the traces and not being afraid to plug numbers in and seeing what kind of shapes that I get, right? And then trying to visualize that before just running to GeoGebra to help with it, right? I'd like you to develop some intuition as you work with this, right? Being able to say, let me check the traces here. What is it this way? What does it look like this way? And what does it look like this way? Right? And that usually can give you some good information about what the surface looks like, right? Let's do another one. This one's going to end up being called a hyperboloid of one sheet. Okay, so let's see. Fancy name, but let's see what we can do with it. So hyperboloid of one sheet. Okay. Now the form for that is x squared over a squared plus y squared over b squared minus z squared over c squared equals 1. Okay? So let's investigate the traces on this a little bit, right? So I'm going to do the same idea here. I'm going to say trace, right? And let's say that x is 0. If x is 0, that means I'm in the yz plane, right? And in the yz plane, if x is 0, this is gone, that's a hyperbola. That's a hyperbola, right? Something squared minus something squared equals 1. That's a hyperbola. So we know that it's a hyperbola looking thing in the yz plane. Take y equals 0, the xz plane. If y is 0, that wipes out and gets me a hyperbola. X squared minus z squared equals 1. Yep, another hyperbola. Okay. And then if z is 0, I'm in the xy plane, right, the floor. And if z is 0, notice what sort of shape I get. I get x squared over a squared plus y squared over b squared equals 1, which is an ellipse. Okay, so it's hyperbolic this way, it's hyperbolic this way, right? And it's elliptical in the middle, right, in the xy plane, right? So it's like hyperbolic, hyperbolic, right? And then elliptical in the middle, right? That would look like this. See that? There's the hyperbola in that sense. Here's the hyperbola in the other sense. And then here's the ellipse in the middle. Do you see that? Now, this is not the only form for a hyperboloid of one sheet. The important thing here is that it's two positive terms, plus plus, and one negative. So in other words, if I had negative x squared over a squared plus y squared over b squared plus z squared over c squared, that would also be a hyperboloid of one sheet. Yeah, so it's not specific that it has to, the x and y have to be positive, and this has to be negative or subtracting. Any combination of that, two pluses and a minus, will yield a hyperboloid of one sheet. Yeah. Okay. Now, what if we have one positive term and two subtraction terms? So here we're going to get x squared, oops, they do z squared. Okay, z squared over c squared minus x squared over a squared minus y squared over b squared equals 1. Again, I'd like to look at the traces. Okay. So first things first, if x is 0, that's the yz plane. And if x is 0, that middle term is gone, and what I'm left with is a hyperbola. Okay, that's cool. Hyperbola. When y is 0, that last term is gone, and I get hyperbola. Okay. So xz plane gets hyperbola. And then if z is 0, this term is gone. What do I end up getting? So if the z is 0, what shape does this make? Well, if I try to work with this shape, right, maybe it's an ellipse, because if I multiply this by -1, that'll make this plus and plus. But wait, that changes that to be -1. Wait a minute. Think about this a little further. Isn't this always a negative number? If it's minus something always positive, right? Isn't this guaranteed to be negative? And isn't this guaranteed to be further negative? So you're taking a negative number, going further negative, and that has to equal +1? That is impossible. That is impossible, right? So that's interesting. If I try to make z equal 0, there's no trace. In other words, when I try to intersect this surface with the xy plane, there's nothing there. There is no intersection because it provides a contradiction, right? If z is 0, this is now a negative number, has to equal +1. Well, that's impossible. Now, with that being said, would z equaling 1 work? Would z equaling 2 work? Would z equaling 3 work? Well, theoretically speaking, let's think about this. Do you theoretically think I could pick a z value where eventually this would be bigger than this subtracting, making a positive number, and probably being able to get 1? So you could probably think theoretically there is a z value high enough that'll make this big enough positive, so when I subtract this and subtract this, I can still get +1. At least that seems possible, right? Would you agree with that? So, right? So what we have here is when z is 0, nothing. But there is a z value where I will start to get a shape, right? And once I do get that shape, then that shape is going to end up being elliptical. because this is going to be now a positive number, a big positive number. I'm going to subtract that over, so it's going to be now a big negative number. And so then I will just multiply everything by -1 to get the format I needed. So for z big enough, we get ellipse. Okay, so we get hyperbola like this way. We get hyperbola this way, right? But there's nothing in the middle. There's nothing in this middle. So it starts like up here. So there's a gap. And so they call this the hyperboloid of two sheets. You see that? And it has a gap right there. Right? Eventually, for some z height, I'll start to get surface. And notice when I cut these horizontally with a horizontal plane, I'm going to end up getting an ellipse. Wider and wider ellipses. Right? But there's definitely a gap at z equals 0, and probably more, right? So there's a nice interval of a gap there, right? This is how we handle quadric surfaces, right? We sort of work with the formula and we work with traces, and it's like an investigation almost. It's like investigating how this thing behaves, right? There's a few others here. I'm not going to go through all the detail. There's 3 more, right? Here we have an elliptical cone. An elliptic cone. Oops. And there we go. An elliptic cone, right? And you can see the form there, right? But again, you could figure this out just by making these 0, 0, 0, and then figuring out what sort of shape you have left. We have an elliptic paraboloid. Now we're starting to get to parabolas because notice this is z, not z squared. And the rest are x squared, y squared. So there's that imbalance of power, right? So that imbalance of power means when I make the y 0, I'm going to get a parabola. When I make the x 0, I'm going to get a parabola, right? And so it's parabola this way, it's parabola that way, and it makes this bowl. It makes this bowl, which is known as an elliptic paraboloid, right? And then finally, we have a Pringles chip. I'm not even joking, everyone. Hyperbolic paraboloids, Pringles chips. The chips, Pringles there, looking like the horse saddle, they are literally hyperbolic paraboloids. And they have this equation here. And so that's actually a thing. If you look up Pringles and hyperbolic paraboloid, you will see that people have made that connection, and it's not a surprise. It's not a coincidence that it was designed that way, to be a hyperbolic paraboloid. Yep, and so there's the form for that. And the shape of that surface, yeah? Oh, excuse me. All right. Any questions with what I've been doing there? We doing okay with those sorts of explorations? We doing okay with that? Okay. Basically, I want you to be okay enough to be able to do the matching in the homework, okay? And so let's go on and scroll to the homework here and see how we could interact with that. So scroll, scroll, scroll. Avert your eyes if the scrolling is weird. Okay. And here we have a matching, right? We have a picture, A, B, C, D, E, F, right? And then we have formulas or equations, yeah? And what I want to do is make sure that I match the equation to its picture, to its graph, okay? Let me show you, I'll do a couple of these, but then I want you to be able to really think through the rest, right? So for instance, take 5 here, right? Now 5, if z is 0, I should get an ellipse. So I should get an ellipse in the xy plane. When y is 0, I should get an ellipse in the xz plane. And if x is 0, I should get an ellipse in the yz plane. So this one should be pretty easy to spot. It's going to be an ellipsoid. Ellipses in all 3 senses, in all three orientations. And there's only one picture on here that does that, and that would be C. See that? And so 5 would match with C. Now you can actually take a look here at the numbers to make sure that they work out. Notice what I was saying before when I was saying that y should only go between 4 and -4. And take a look here. Let me zoom in here. It looks like that this goes all the way up to 4 this way and -4, right? 1, 2, oh, y, sorry. I was looking at the wrong axis. Here's the y-axis. Notice how y goes to 1, 2, 3, 4. That's the maximum y could be. And then the minimum y can be is back here, 1, 2, 3, 4. And that's governed by the 16. That's governed by the 16. The x and the z are stuck between 3 and -3. Let's take a look at that. So you can see it easily, I think, here in this vertical. See how it goes 1, 2, 3 units up, 1, 2, 3 units down. And in the x sense, it goes 1, 2, 3, right there. And 1, 2, 3, which is sort of covered up by the light spot there. Okay, but anyway, I was able to match that, right? Now, let's see here. Can I take another one of these? Let's do an even one, so I don't steal an even one from you. Let's do 10. Let's do 10. See if which one's is 10 here. Okay, so I'm going to jot down 10 and then figure out its traces. So 10 is 4x squared minus y squared plus 4z equals 0. And I want to just work out the traces and then explore what the picture should be. Okay, so let's go ahead and take this on paper. So I'm going to explore the traces. So here we go. If x is 0 in the yz plane, all right, in the yz plane, I would get negative y squared plus 4z equals 0. Which is to say that I get 4z equals y squared. That is a parabola, right? So I get a parabola when I intersect this surface with the xy plane. So I should get a parabola. And in fact, y can be positive or negative, but squaring y guarantees that this is positive. So that's also really good information here, right? So what this is saying is when I intersect this surface with the xy plane, or sorry, with the yz plane, I should not have any negative z values. Should not have any negative z values. Let's go ahead and make some more observations. Y equals 0. If y is 0, then I get in the xz plane. Here's what happens. If y is 0, I get 4x squared plus 4z equals 0. Right? Now, working with this a little bit, let's see what I end up getting. I get 4z equals negative 4x squared. Okay? And the 4's can cancel, but I definitely get a parabola here. Right? But it's interesting because x can be plus or minus, and it's squared, but then there's a forced negative. So here, the z's are going to be negative. So this is a parabola, and z is going to be negative. This parabola, z is going to be positive. This way of cutting this, z is going to be negative. Okay. Let me get the last one down on paper, and then we'll start hopefully piecing this together. So here, z equals 0 in the xy plane. If z is 0, oh, I glitched, sorry, yeah. So repeat the last one here. Repeat this, basically. Okay. So yeah, what we have here is that z, okay, is going to be negative x squared, which means that when I intersect this surface with the xz plane, which is the left wall, I am going to get a parabola, but it's going to open downward because z's are negative. right? So when I intersect it this way, I'm going to get a downward parabola. Okay. Likewise, when I look at this one, when I cut this with the YZ plane, which is the plane this way, I'm actually going to get a positive parabola. So it's going to be positive this way, like this, right? But it's going to be negative this way. What a funky sounding or looking surface. Okay, final check here. Z equals 0. If z is 0, I end up getting 4x squared minus y squared equals 0, right? Because z is 0. And this is basically why I wanted to do this problem, because look, this actually ends up being what? 4x squared equals y squared. And taking the square root of both sides ends up getting me 2x equals plus or minus y. Taking the square root of both sides there, right, gets me 2x equaling the plus or minus of y. Right? These are straight lines. Oh my goodness. So when I intersect this with the floor, I should get straight lines. All right. Are we ready for the pictures? Let's do it. So have this in mind. I think the parabolas are going to be the key to figuring this out, right? So let's go ahead and now bring back the pictures. Okay. This one is out because notice this one, there's nothing intersecting the XZ plane, and that would have spotted when y equals 0, we would not have gotten a trace. So E is out. F has hyperbolas here, and so we did not get hyperbolas as traces, so F is out. We're looking for parabolas and lines. Here we have parabola, and here we have a parabola, but it's not doing the positive negative thing that I was mentioning here, right? And in fact, y is always positive here, and we did not get that fact there. We got that y could totally be positive or negative. It was the z that had to be positive in the YZ plane. That's not it. That's not the picture. We already picked that one. That's not the picture. Here we have lines, but that intersection there is supposed to be a parabola with that. So this isn't the picture either. It's got to be this one. And so we have a Pringles chip. This is a hyperbolic paraboloid. Yeah? And so check this out. We have parabola opening up when intersected with the YZ plane. Right? We have a parabola opening downward when intersected with the XZ plane. And this is harder to see because they've not drawn it, but you do end up getting a line, diagonal lines, when you cross this with the XY plane. They've not drawn those, but those lines would be like diagonal coming out of here and coming out of there, and then going back through the screen and then up forward through the screen as well. Yeah, so that is A. By method of deduction and by like confirming at least the traces are all possible and are all there, right? So I have confirmed that problem 10 is matched with A. All right? I'd let you do the other 4 because this is one of those problems where if I just tell you, you'll be like, sure, yeah, I get it. But you really need to do your own sort of figuring out on this. Doesn't that make sense? Yeah. Like if I just tell you what the answer is, that's not going to help you. You want to construct your own answer and your own justification for these others, right? I promise you can find all of these matches by doing the trace argument, by doing the trace thing that we've been doing. Okay. And so I'd like to move on unless there's any other questions that you might have for me on 11.6. That finishes 11.6. Okay. You know what? It's a little early, but I think I'm going to cut it off there because I don't want to start a brand new topic because the next section is sort of a brand new topic talking about coordinate systems. So if you'll forgive me, I think I'll stop there for the evening, and we can start fresh on Tuesday with a fresh topic on coordinate systems. We're going to talk about you've heard of polar coordinates, right? You've heard of polar coordinates, which is a two-dimensional coordinate system, right? Using angle and distance, right? R and theta. Well, now I want to get some other coordinate systems that are super useful for 3 dimensions, right? And so we're going to learn cylindrical coordinates and spherical coordinates. Super useful for anything you want to describe in motion and space, especially if they have orbits or move in a parallel way to something or rotate or something like that. These are going to be handier coordinate systems to work in, right? You're not stuck having to always do X, Y, Z, right? Rectangular motion is great. It's pretty easy, except when you're doing something complex like spinning, right? Rotating, moving. And now I'm trying to move circularly through a space that's being measured by rectangular things. Doesn't seem to be the proper tool to do that. So we will develop a couple tools that we can describe these motions in space using different coordinate systems. So we'll introduce those coordinate systems next time and get to working with those. And in chapter 12, we will start working with those coordinate systems on describing motion, on how we can use vectors to describe velocities and accelerations of objects. And so really good practical stuff. And if you're trying to figure out how things change, how things move, how things interact with other things, these are the common tools that we can use. All right. So everyone, hope you're doing really well. Hope you had a great Labor Day. Hope you continue to have a good week, and hope you have a great weekend. And looking forward to checking in with all of you on Tuesday. And until then, I hope you're feeling better. Those of you who are sick, somebody in chat was like, I'm not feeling good today. So hopefully you're feeling better real soon. And I hope you're all taking care of yourselves, taking care of each other, and looking forward to checking in with you next week. All right. Till then, be well. See ya.